Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the pleasure of presenting a public lecture by Dr. Clifford Jack from the Mayo Clinic in Rochester, Minnesota, entitled Evolution of Systems for Diagnosis and Staging Alzheimer's Disease. Dr. Jack is a professor of radiology in the area of neuroradiology and the Alexander Family Professor of Alzheimer's Disease Research at the Mayo Clinic. His Aging and Dementia Imaging Research, or ADIR laboratory, conducts brain imaging studies focused on cognitive aging and Alzheimer's disease and related disorders. The group's work examines how imaging measures relate to neuropathology, fluid biomarkers, genetics, and cognitive and behavioral characteristics. The ADIR team also serves as the magnetic resonance center for several large multi-site observational and interventional research studies. Renowned for his pioneering contributions to Alzheimer's research and neuroimaging, Dr. Jack has received many honors, including election to the National Academy of Medicine, the Henry Wisniewski Lifetime Achievement Award, the Potemkin Prize, and the MetLife Foundation Award for Medical Research. If you have any questions during this talk, please type them into the chat or question and answer dialog box. And at this time, it is my great pleasure to introduce Dr. Jack.
Thanks very much for the kind introduction, Dean, and thanks for inviting me to give this talk. Hopefully, I work in a fairly specialized area. Hopefully, what I have to say will be of some interest to a more general audience. So what I'll talk about, in the title that Dean mentioned is, I should also mention I'm walking in a treadmill. So I'm in my office and I have a treadmill desk and this is what I do all day. So Dean said, okay, go ahead and walk while you give your talk. So the wobbling back and forth is not too distracting, hopefully. So what I'll talk about then is this title, Evolution of Systems for Diagnosis, Definition, and Staging. And you'll notice that diagnosis and definition are coupled together. And there's a reason for this. And that is that how one diagnoses a disease operationally, in fact, turns out to be how one defines a disease. And this has actually been pretty controversial in recent years in the area of Alzheimer's disease. And hopefully you'll see why over the next few minutes. So this is the talk. I'll give a little bit of a history about diagnosis, definition of Alzheimer's disease, talk about a recent criteria from the Alzheimer's Association, address some controversies, and then talk about this notion of risk. So what does the term Alzheimer's disease mean? Now, this might seem like a very odd thing to even propose. Surely experts in this area all agree on what Alzheimer's disease is. There's no controversy, but that's in fact not true. So most people, probably most people in the general public are at least vaguely familiar with this idea of plaques and tangles. So this is what an amyloid plaque looks like at autopsy. This is what a neurofibrillary tangle looks like. These are the two proteinopathies that define Alzheimer's disease. So the primary constituent of amyloid plaques or CNI plaques is beta amyloid, aggregator beta amyloid protein, and the primary constituent of neurofibrillary tangles then is the tau protein. So really everyone in medicine, everyone in medical research agrees that this is indeed the neuropathology of Alzheimer's disease. But how does one then diagnose or identify Alzheimer's disease in the living patient? And for that, we go back to, I would say, the 1980s. And it'll be apparent why I bring this up in a second. This is a slide from my colleague in behavioral neurology here at Mayo, Dave Notman. And he, I think, nicely articulates how experts in the field of Alzheimer's disease thought about the relationship between the underlying brain pathology that was called Alzheimer's disease and the related clinical symptoms. So the thinking in the 1980s was this sort of two-state view, which was that if an individual was cognitively normal in life and then came to autopsy, they would be expected to have no Alzheimer's pathology in the brain at autopsy. On the other hand, if they were demented and met certain clinical criteria, they would be expected to have Alzheimer's disease at neuropathology. And why is that important? It's because in that time frame, 1980s, the first widely accepted, and in fact, in many circles, still used today, in vivo criteria to define Alzheimer's disease were these so-called NANCDS, ADRDA criteria. And these criteria held that a diagnosis of probable Alzheimer's disease could be made in life after certain exclusions based solely on clinical presentation, whereas a diagnosis of definite Alzheimer's disease required autopsy confirmation. Unfortunately, what happened over time was that an amnestic dementia, so amnestic refers to a memory problems, no surprise, and amnestic dementia became equated with Alzheimer's disease. In other words, amnestic dementia, which is a clinical phenotype or a clinical presentation, became equated with one specific neuropathology. Now, what's wrong with this? What's wrong with this is illustrated in this slide. And this is a slide from my colleague, Ron Peterson here at Mayo Clinic, also in behavioral neurology. And the fundamental problem with this idea of a clinical pathologic definition is it does not recognize the existence of preclinical disease. In other words, if you have to have clinical symptoms in order to have a disease, then there is no such thing as brain disease which precedes the onset of clinical symptoms. Furthermore, it's not specific. And what do I mean by that? So this slide illustrates this notion that actually there are several different common pathologies that underlie most of what you see in older people who become cognitively impaired, whether they're mildly impaired, which is called MCI, mild cognitive impairment, or whether they're fully demented, which means that an individual has a cognitive impairment that is severe enough that they require assistance, to some degree of assistance with activities of daily living. In other words, cognitive impairment is so severe that they've lost independence. But Alzheimer's disease is surely a common contributor. But most people who, in fact, become cognitively impaired in old age have some mix of Alzheimer's disease, another proteinopathy called TDP. We will get into it, alpha-synuclein, which is the proteinopathy that underlies Lewy body disease, and then vascular disease. And so a clinical presentation of a progressive, largely memory dominant, but ultimately involving several different cognitive domains that ultimately leads to impairment is not specific for just one of these, Alzheimer's disease. Now, for many years, to be honest with you, it really didn't matter a lot. And why didn't it matter? And that's because there was no treatment for Alzheimer's disease. If there's no treatment, then a precise biologically based diagnosis really had no direct clinical impact. However, when the pharmaceutical industry began targeting specific pathology, Alzheimer's pathology, for intervention, then this notion of a clinical definition of Alzheimer's disease really became hugely problematic. And I've cut and pasted the base pages of the first two large phase 3 clinical trials that were designed to specifically target and remove amyloid plaques from the brain of patients with Alzheimer's disease. Both of these trials failed. They did not meet their endpoints. And in subsets of individuals in these trials who underwent amyloid PET imaging, so people were enrolled in these trials based on the 1984 clinical only criteria. In other words, a progressive, largely memory problem. And what happened in subsets that underwent amyloid PET imaging was about 30% of the individuals enrolled in these phase 3 trials did not have Alzheimer's disease. They had other causes for their underlying cognitive impairment. And I think you can make a very principled case that if you indeed are attempting to modify the underlying course of the disease process, that is, remove or slow down the underlying pathology, that if you have a treatment that has a modest therapeutic effect, which is the case with these monoclonal anti-amyloid antibodies, it would be impossible to get a phase 3 trial that was successful. And both of these trials did indeed fail. So what is the answer to the problem? The answer to the problem is biomarkers. Of course, biomarkers are indicators of normal or abnormal underlying physiology. And the first biomarkers for Alzheimer's disease, you can kind of think of the era of the biomarker era of Alzheimer's disease beginning sometime around the 2000s. I've cut and pasted examples of some of the earliest literature. This is a cerebrospinal fluid. So in other words, one takes a sample of the cerebrospinal fluid and looks for the concentration of different proteins, tau and A-beta and amyloid beta proteins, or amyloid PET imaging, which was a really groundbreaking development by Bill Klunk and Chet Mathis at the University of Pittsburgh. But this sort of marks, if you will, the earliest era of biomarkers in Alzheimer's disease. Notice, though, that these biomarkers were both either invasive, so cerebrospinal fluid, which requires that you put a needle in the lumbar spine, remove cerebrospinal fluid, which is obviously invasive, and then PET or PET imaging. PET imaging is expensive and not widely available. So the early era of biomarkers in Alzheimer's disease worked, but it was either invasive or expensive. Now, some of the earliest work, this is PET imaging in Alzheimer's disease. And you can see some of our very early studies after the invention of PET by Bill Klunk and Chet Mathis, amyloid PET. You can see a negative looking amyloid PET scan. That CU stands for cognitively unimpaired, a very abnormal amyloid PET scan with lots of uptake throughout the cortex in someone who has dementia. But you also see in an unimpaired individual a fairly large amount of amyloid PET uptake. And this was inconsistent with the notion that undergirded the existing clinical definition of Alzheimer's disease at the time, because here you have clear evidence of a lot of amyloid pathology in someone who has no dementia at all. We and others at the time, this is in the early 2000s, yeah, also started to look at not just amyloid PET imaging, but multiple different imaging types. And what you see here are the annual rates of change, annualized rates of change on the y-axis in 3 different groups of people: cognitively normal, mildly impaired, and fully demented. This is amyloid PET on the left, and this is the delta in brain volume. And what you can see here is, again, something very unexpected, given the prevailing view of Alzheimer's disease at the time. And that is, you see basically no relationship between the rate of change in this amyloid PET biomarker, which is specific for Alzheimer's disease, and the rate of cognitive change in these different clinical groups. So the rate of cognitive change in CN, unimpaired people, is pretty low. It's a little bit higher in mildly impaired people, and it's very high. So you see no relationship. On the other hand, with this marker of brain atrophy, you see a very nice relationship between the contemporaneous rate of clinical decline and the decline in brain volume. So again, this did not match clinical thinking at the time. One would expect a very good relationship between change in amyloid PET and cognitive symptoms, which you can see is actually not true. So this then led to different models that differed pretty substantially from the old 1984 view of Alzheimer's disease. And this is a model several of us put together back 20, 15 or more years ago now. And this model can be illustrated in this way. So on the y-axis, you can see the magnitude of various biomarker abnormalities, going from normal to abnormal. And on the x-axis, you can see time for different clinical stages. So early on, cognitively normal, then MCI mildly impaired, and then later on, fully demented. And the idea here is that you can see different biomarkers. So biomarkers of amyloid plaques, biomarkers of tau-mediated brain injury, etc. And the idea that this graph is intended to display is that there is a staggered but overlapping onset and then progression of biomarkers of different aspects of pathology. And these become abnormal while an individual is still cognitively normal, unimpaired. So this is completely different from the traditional way to think about Alzheimer's disease at the time. And then I would say that there are two different groups, working groups, that have put out modified or updated clinical criteria, diagnostic criteria for Alzheimer's disease over time. I'll concentrate here for the time being on a group led by the National Institute on Aging and the Alzheimer's Association. Talk a little bit about the second group in a minute. But in 2011 then, recognizing the importance of biomarkers in the diagnostic process, the NIAAA convened three separate committees, which published three different sets of guidelines, one for preclinical disease, one for mild impairment, and one for dementia. And these are really the first sort of US-based diagnostic criteria that had been modernized to incorporate biomarkers. But you can see three separate committees, three separate sets of guidelines. You can already maybe anticipate that there are going to be problems here. And indeed, there were some problems with this, which I'll talk about more in a second. But three different committees, there were some pretty obvious inconsistencies between these different criteria conceptually that eventually became problematic. Now, another important development in the field was the development of tau PET. And you start to see a theme working out here. And that is that diagnostic criteria for Alzheimer's disease are being changed or modified over time as new scientific developments come online. And this was the development of tau PET. So recall the two main pathologies in Alzheimer's disease are beta amyloid plaques and tau tangles. Before this work, which was led by Hartmut Kohl, there was no way to really successfully image tau tangles in the brain. But with this development then, a group of us decided that it was actually probably time to rethink about how different biomarkers for Alzheimer's disease should be classified. At the time, there was no coherent classification scheme for different Alzheimer's disease biomarkers. And so this group of us proposed that different markers should be lumped into these groups of biomarkers of the underlying amyloid beta pathology and T, that's A, biomarkers of tau pathology, neurofibrillary tangles, and then biomarkers of neurodegeneration. This led to this notion of ATN, biomarker grouping. And you can see I've listed in 2016 at least, these were the available biomarkers that would be slotted into each of these three different mechanistic categories, A, T, and N. And this ATN biomarker classification scheme actually has become very widely used in the Alzheimer's research field. Now, in 2018, the NIA and Alzheimer's Association decided leadership decided that actually the old 2011 criteria needed to be upgraded for several different reasons. But one was to incorporate this notion of ATN biomarker staging into modernized criteria. And secondly, to unify, perhaps more importantly, to unify the definition of across its continuum. So recall in 2011, there were 3 different work groups, 3 different position papers defining different stages, clinical stages of the disease, but that was misinterpreted across pretty wide swaths of the field to mean, oh, there's 3 different diseases. And so in 2018, we unified the definition of Alzheimer's disease across the entire clinical and biological spectrum. I've just cut and pasted one of the graphs from that paper. And I've circled this. You can see a cognitive stage, unimpaired, mildly impaired, fully demented. In the columns and in the rows, you can see the different permutations of A, T, and N, plus or minus, meaning normal, abnormal. And the point here is that I've circled in red is the idea of unifying the definition of Alzheimer's disease, which at the time we took to mean evidence of amyloid plaques A plus and tau tangles T minus, T plus. Anyone who met these biologic criteria would have the disease, and it doesn't matter if you are cognitively normal, mildly impaired, or fully demented. The disease was defined by its underlying biology. Now, this was very controversial at the time. Actually, it's still controversial in some circles today. But this was the position, these were the 2018 NIA criteria. Now I'll turn to the 2024 Alzheimer's Association criteria. This is the face page of this work group, the revised criteria, which we just published 2024, so a couple years ago. So why did we decide to update the 2018 Alzheimer's Association criteria? And again, this theme of new technical developments, which motivate the modification or update of diagnostic criteria. And one of the main technical developments that's occurred over the past couple of years is the development of plasma biomarkers. Some of which, not all of them, but some of which really have very excellent diagnostic performance, which is on a par with assays, cerebrospinal fluid-based assays that have been approved by the FDA and are used widely in clinical practice. Plasma, as you can imagine, is much more accessible. It's just simply a blood draw, as opposed to having to put a needle in the lumbar spine and withdraw CSF. For plasma biomarkers, then, really open up the biologic definition of Alzheimer's disease to essentially the entire population. Indeed, anywhere in the world, you simply do a standard blood draw, very non-invasive. You can send it to a lab, a central lab. So this was and continues to be a major breakthrough just recently in the diagnosis of Alzheimer's. The second major development was that by 2024, there had been treatments that had been approved by the FDA that actually target and successfully remove one of the main pathologies, one of the 2 main pathologies in Alzheimer's disease. And people are probably well aware now that there are now anti-amyloid monoclonal antibodies that do indeed target and remove amyloid plaques and result in a slowing in the rate of cognitive decline in individuals who are cognitively impaired. That's the only group that these drugs are approved for now. But this is really 2 very landmark changes: diagnosis by plasma biomarkers, and now treatments that actually, for the first time in history, have some effect on the underlying progression of the disease. So a brief overview then of these, the most recently updated set of Alzheimer's Association criteria 2024, and that is the concept of separating the syndrome, that is the clinical presentation, from the underlying pathobiology, that is Secondly, as in 2018, in 2024, we define Alzheimer's disease as a biological process that's identified by what we call core biomarkers. Alzheimer's disease is a continuum that begins with the appearance of brain pathology many years before, while people are asymptomatic, and that's many years before people become symptomatic. We define diagnosis by early changing core 1 biomarkers, which I'll illustrate in a second. Biological staging by a combination of core 1 and core 2 biomarkers, where core 2 are later changing biomarkers, and then we integrate these two concepts. So core 1 versus core 2. This is an updated version of the graph I showed earlier. Again, you see time on the x-axis. You can see the magnitude of different biomarker abnormalities on the y-axis, from minimally abnormal and normal to maximally abnormal. And the core 1 biomarkers are simply this group of biomarkers, either A beta fluid, could be CSF, or more recently plasma, amyloid PET, or another early changing biomarker, plasma biomarker, phosphorylated tau, so-called p-tau. These change early. They remain abnormal through the duration of the disease. And so these are logical biomarkers to use for diagnosis. Core 2 biomarkers are biomarkers that denote the actual tau pathology. So these are biomarkers that denote the spread of tau tangles throughout the brain. You can see they become abnormal later in the disease process, much closer to the onset of clinical symptoms, which you can see here at the far right hand, being the last thing to change, if you will, the last thing to show up in the in this progression. And then it's the combination of the magnitude of core 1 and the magnitude of core 2 biomarkers that can be used to stage the biologic severity of Alzheimer's disease. That brings me to the next aspect then of these updated diagnostic criteria 2024, and that is we actually propose a formal biologic staging scheme. We have 4 stages, A, B, C, D. I won't get into a lot of the details here, but these, and you can see that these are denoted by different PET scans, so amyloid PET and tau PET. And this staging scheme actually corresponds very tightly with neuropathologic severity staging that has been widely accepted and has been used to stage the disease after death for many years, decades. We also have a clinical staging scheme. So clinical staging is only applicable in individuals who have biologic evidence of the disease. There's a stage 0 for people who have deterministic genes. I won't talk much about that, but clinical staging of Alzheimer's disease is only applicable for individuals who have biomarker evidence of the disease. And stage 1 then is a pretty long-lasting stage. That is, people are completely asymptomatic with only core 1 biomarker evidence of the disease. Stage 2 is something we call transitional decline. So this is when clinical changes are mild, but they really have no impact on daily function. Stage 3 then would be what would be consistent with mild cognitive impairment. And it really is stage 3 that denotes the earliest clinical stage that today would make someone eligible for treatment. So the drugs that have been approved, 2 monoclonal antibodies, one called donanemab, you might have heard of it, another one called lecanemab. But these have been approved by the FDA and not only in the United States, but actually in countries in Europe and Asia as well. Someone has to be in stage 3 before the regulatory agencies have said this is the earliest clinical stage that you can treat Alzheimer's disease. And I'll get to why this is, I'll get to this sort of notion of the earliest stage of treatment in a little bit. And then stage 4, 5, and 6 simply represent mild, moderate, and severe functional impairment, more advanced stages of the disease. So in stage 6, this would be someone who is completely dependent on others for care. Typically, these people are in care facilities, nursing homes, etc., and are completely unable then to take care of themselves. And then we integrate biological and clinical staging. So you can see clinical stages in the columns here, and biological stages, A, B, C, D, in the rows. And the integrated staging are these alphanumeric characters you see in the cells in this table. And we deliberately arrayed clinical in the integrated biological and clinical staging in the 2024 diagnostic criteria in this manner, sort of orthogonal manner, to illustrate several important principles. One is that biological staging, so the severity of biology and the severity of clinical presentation, often travel in lockstep. That is, you can see is this trajectory from 1A down to the top left to the bottom right, where clinical severity and biological severity track in a lockstep. That's a sort of typical presentation, but very often in the population, you'll see divergence from this tight coupling between clinical and biological stages. So people who sit above this diagonal line are individuals who have worse clinical presentation than you would expect for their Alzheimer's disease biological staging. And this is actually very common. And the most common underlying rationale here is that these individuals who have other pathologies, for example, multiple strokes, etc., that are driving their cognitive impairment independent from Alzheimer's disease. So they have worse clinical presentation than you would expect given their Alzheimer's biological stage. And then in the lower right set of columns, you have people who have better clinical presentation than you'd expect for their underlying biological stage. And these are individuals who have exceptional cognitive resilience or reserve, be it genetic or the result of lifetime exposure to higher education, challenging jobs, etc. These are individuals who cognitively are able to continue to perform, if you will, despite the fact that they have significant Alzheimer's pathology. So in summary then, these 2024 most modern Alzheimer's Association diagnostic criteria I'll skip that slide for the time being. So let me turn now to this notion of controversies. So really there are three perspectives on this notion of a biological definition of Alzheimer's disease. That is defining the disease purely based on the pathology in the brain, not on the basis of clinical symptoms. There are three perspectives, and one is that there are people in the field, and probably most of the general public just still thinks that Alzheimer's disease is equivalent to dementia. So Alzheimer's disease means someone can no longer think for themselves, they lose their capacity for self-care, etc. And that's what Alzheimer's disease is. And there are plenty of people in medicine who still take this view. The second group, I mentioned earlier that there are really two groups, I won't say competing, but kind of, that have created a series of criteria over the years. I've been describing the Alzheimer's Association, but there's also an international work group that takes a different position. And that is that you have to have positive biomarkers plus clinical symptoms in order to use the term Alzheimer's disease. The Alzheimer's Association criteria, on the other hand, recognizes that the disease begins in the brain many years before onset of symptoms, and that Alzheimer's disease is a biological construct. And people even completely outside this field may be aware of the controversy. So the controversy between these two groups, the IWG and the Alzheimer's Association. There have been many editorials in the scientific literature arguing one way versus the other. There have been many very heated arguments at scientific meetings. And in fact, this has escalated to the lay press. So there have been a number of articles in the lay press arguing one side versus the other. And when you come right down to it, these two groups, the IWG and the Alzheimer's Association criteria, are not all that different. And there are a number of ways that they're really identical. They both recognize that the pathology begins in the brain years before symptoms. They both assert that you have to have biomarkers of Alzheimer's pathology if you want to diagnose Alzheimer's disease. They both recommend against biomarker testing today in asymptomatic purposes for clinical purposes because there are no approved treatments for asymptomatic individuals with the disease. But there's one huge difference, and that is that an asymptomatic individual with a positive core1 biomarker, the IWG would say these people are at risk for Alzheimer's disease, whereas the Alzheimer's Association would say no, these individuals have the disease, but they're at risk for developing symptoms from that disease. And this is a simple way to visualize the discrepancy between these two different sets of diagnostic criteria that exist today. And that is this very long period of time from the onset of biomarkers, denoted by the red line, to the onset of clinical symptoms, denoted by the purple line here. This roughly 15-year period of time, the Alzheimer's Association says the person has a disease, they're at risk for symptoms. The IWG would say, no, they do not have a disease, they're at risk for a disease. And this may seem trivial, but there is actually some importance to labeling a disease in terms of achieving regulatory approval for intervention. It becomes difficult to achieve regulatory approval for interventions if you don't identify that the treatment is targeting a disease. So this agreement, which there's been a lot of press about, may seem trivial, and in some sense it is trivial. It's just about terminology, but it does have important ramifications. And so when you come right down to it, what is really the source of this controversy? And that is that it is a fact that some proportion of unimpaired biomarker positive individuals will die of other causes without ever experiencing symptoms. The rate of all-cause mortality increases exponentially with age. So a lot of people will indeed die asymptomatic with what we would say is Alzheimer's disease in the brain. And from a scientific perspective, this comes down to the question, what is the lifetime risk of impairment associated with abnormal Alzheimer's biomarkers? And this is termed absolute risk. That's what I'll talk about for the remaining few minutes here. Risk of cognitive impairment. So absolute versus relative risk. And hopefully it'll be clear why this is very important in a second. So relative risk is as a hazard ratio. In other words, it's the event rate, the rate of becoming demented or becoming mildly impaired in a target group. Let's say a target group would be someone with an abnormal Alzheimer's disease biomarker versus a reference group. That would be the rate in, let's say, someone without an abnormal Alzheimer's biomarker. It's a comparison in event rates between two groups. Absolute risk, on the other hand, is the likelihood in percentage terms that someone will experience an outcome over a specified period. So it could be 5-year, 10-year, or lifetime. But absolute risk is a percent. It is calculated as the number of people who will experience the event over the total number at risk. This is the number that is clinically meaningful. Relative risk, not so much, but the percent likelihood that someone will become dementia if they have a positive Alzheimer's biomarker is really the value that's needed, the data that's needed to address this controversy. And you have to account for the competing risk of unrelated mortality to do this calculation. But why am I mentioning this? And that's because despite the fact that this is the statistic, this is the data that's really needed to get a handle on this controversy, there's almost no evidence in literature about absolute risk of dementia or mild cognitive impairment associated with Alzheimer's biomarkers. And why is this? It seems very strange. If there's such a big need for this data or for this information, why wouldn't there be tons of studies on this? But let's look at where this information comes from. So the information about cognitive risk associated with Alzheimer's biomarker comes from longitudinal observational cohort studies that have embedded in them deep clinical phenotyping and also Alzheimer's biomarkers. And recall that until very recently, the only Alzheimer's biomarkers that were available really were either very invasive, requiring a lumbar puncture, or were very expensive, requiring PET scans. So this is not data that's just routinely available in huge chunks of the cognitively normal elderly population. These have to be very specifically designed, expensive, long-term studies. And in these studies, it turns out that the competing risk, you have to compute the competing risk of death in order to compute absolute risk. This is actually not captured in most of these longitudinal studies. Moreover, you have to count all incident impairment events and all deaths. The problem is that in these longitudinal studies, people don't stay in the studies forever. So recall the time scale. From the time of onset of abnormal biomarkers to onset of clinical symptoms might be 15 years. And because these studies are fairly early forms, they require every year or every couple of years detailed hours-long cognitive assessments and PET scans. People tend to drop out. And once people drop out, then you lose the ability to capture these impairment events in these groups of people. So we recently published a study designed to try to fill this knowledge gap. And that is, what is the lifetime risk of impairment associated with biomarker positive individuals? And these are the data. I won't go through all the features of our study, but basically all the flaws or problems that I mentioned before, that is not being able to capture incident dementia, incident impairment in people who've left the study. We found a way to fix that, to identify that data. And these are the data that we come up with. And on the x-axis, you see magnitude of amyloid PET values. So centiloid is a continuous scale of amyloid PET abnormality, 5 being a very normal value, 100 being a very abnormal value. And on the y-axis, you can see that the proportion of individuals who, in these different categories, who had an event. So on the left-hand side, you can see lifetime risk. On the right-hand side, you can see 10-year risk. And we've identified 4 different groups of people here. One is in the blue. You can see, so apolipoprotein E is the major genetic risk factor for late onset sporadic Alzheimer's disease. And so you can see carrier, non-carrier, male or female, that results in 4 different groups. And so you can see here the at the top, the lifetime risk of incident mild cognitive impairment for male non-carriers here, for female carriers here, and male carriers and female non-carriers pretty much overlap. And you can see the risk increases from very normal amyloid PET values to high amyloid PET values. This is the lifetime risk of dementia. You can see the same sort of stratification of risk by groups, exactly the same pattern. You can see that overall, if you pick a given centiloid value, the lifetime risk of dementia is around 20% less than the lifetime risk of mild cognitive impairment, which makes sense because everyone who develops dementia has to first develop mild cognitive impairment. But some people with MCI will die without ever becoming demented. Hence the higher lifetime risk of MCI. For 10-year risk, it's actually very interesting because for 10-year risk, you've constrained the time window. So no longer lifetime. The question here is, what is the absolute risk in percentage terms of developing MCI at the top, dementia at the bottom, as a function of amyloid PET on the x-axis, and then different ages. So 85 years old at the top, 60, 75 starting age in blue, and in red you have age 65. And so why is there this dramatic difference in the risk associated with the 10-year risk, but actually not so much for lifetime risk? And the answer is that both death rates and dementia rates increase dramatically with age. So someone who is 85 has a much higher risk because the rate of dementia is much higher for 85-year-olds as compared to 65-year-olds over a 10-year time period. It's not so, however, for lifetime risk. And the reason is that while the rate of dementia is much higher for an 85-year-old, a 65-year-old has many years left to become demented, an 85-year-old not so much. So it's a very interesting result. But these statistics then are really the first statistics to sort of flesh out this notion of absolute risk, lifetime risk, and 10-year risk associated with Alzheimer's disease pathology, severity, and also these other risk factors, sex, and being a carrier of apolipoprotein E. And so what we've done is we've created an online prediction app, which I've copied and pasted this here. You can see this is the link right at the top. If you go into this link, you'll see this information here, which is pretty much disclaimer about don't use it for clinical purposes, use it for research. You have to click, I acknowledge, and if you do, then this calculation will come in. And I've pre-filled in some values. So, for example, a female, an ApoE4 carrier, let's say an amyloid PET centiloid level of 55, which is clearly abnormal, but not wildly abnormal. And then let's say a current age of 74.5, you hit calculate. And here, then you get estimates of risk going forward years from current age on the x-axis, and on the y-axis, you have the probability that an individual who has these input values of sex, current age, amyloid PET value, and their genotype will ever develop MCI at the top or ever develop dementia as a function of increasing time from current age. And these are the exact numbers here in these columns, but this graph shows this function. So some conclusions then about absolute risk. So one, the risk for both MCI and dementia increases with the severity of Alzheimer's disease. Hence the importance of knowing this information going forward. Secondly, the lifetime risk of, for example, MCI can be very high in the highest risk groups. Third, the lifetime risk varies considerably among individuals who would be considered amyloid positive. So in other words, this notion of your biomarker being normal or abnormal really throws away or discards very valuable predictive information. And the results of this study clearly show that this is not how, going forward, people should think about Alzheimer's disease biomarkers. They should be scored as continuous measures. No surprise, someone's genetics adds to biomarker severity as a predictor. Overall female risk slightly greater than male. And interesting, not perhaps so surprising, but age is the biggest predictor for 10-year risk, not so for lifetime. So why is this important? Why is this notion of risk important clinically? Being able to predict risk important clinically, beyond this notion of settling academic squabbles between people in academia. So I mentioned earlier, at present, anti-amyloid monoclonal antibodies have been approved for treatment in biomarker positive symptomatic individuals. But going forward, it will be critical to treat the disease before the onset of symptoms. And why is that? And the reality is that once someone develops symptoms, those symptoms are never going to get better. The best you could possibly do is arrest the rate of decline. So once someone becomes symptomatic, like I said, symptoms are not going to improve an individual. And what is the underlying basis of symptoms? Really, the underlying basis of symptoms is dead neurons. So it is important to identify the disease prior to the onset of symptoms, which indicates that substantial death of neurons have already occurred. And this is going to be important. There are 2 major phase 3 clinical trials that are scheduled to read out in the next several years. One for lecanemab, one for donanemab. And if either of these are successful, that will open up the door to treating people prior to the onset of symptoms who are biomarker positive. And you can imagine that this will raise a whole number of new issues that medicine has heretofore not had to deal with. And that is, how does one go about effectively screening the cognitively normal elderly population? What age do you start? How frequently do you test with plasma biomarker? What level of plasma biomarker would constitute sufficient evidence to warrant treating someone? And ultimately, the decision to treat or not treat a cognitively normal individual is going to have to rest with the balancing the absolute risk of onset of symptoms, hence the importance of having this information, against potential therapeutic benefit and the risk of treatment complications. So in summary then, that's my last slide. And I hope that I've illustrated a couple things. And one is that the criteria for diagnosis and staging Alzheimer's disease, yes, there are controversies, which I tried to explain, but these criteria are going to always continue to evolve over time with scientific advances. And if nothing else, the disagreement in these criteria that exist today could be taken just as evidence that it's a product of recent scientific advances that people haven't quite gotten to process yet. I do think, however, that the Alzheimer's criteria, where the disease is defined to be a biological process that begins while people are asymptomatic, will ultimately be important indefinitely, forever in the future. And finally, this notion of the importance of getting accurate estimates of individual levels of absolute risk will be important for clinical practice well beyond academic arguments. So I'll stop there, and thank you very much, Dean, for inviting me to give this presentation. Hopefully it was of interest to a more general audience.
Thank you very much, Dr. Jack. That was a very, very nice talk on an important subject, and I'm sure there must be questions. Go ahead and type into the question answer dialog box if you have a question. I see a question by Olivier Masson, who writes, in addition to plasma biomarkers, what about hormones, gut dysbiosis, autoimmune diseases, etc.?
So, okay, I can take a couple of these things. So right now, people who are being treated for an autoimmune, for people who are receiving certain classes of treatments for autoimmune disease, um, specifically monoclonal antibodies are one class of treatment for certain autoimmune diseases. These are contraindications to treatment currently. The reason is because the idea that giving individuals externally derived monoclonal antibodies for two different disease processes at the same time might interfere with each other. So right now, that's a contraindication that may change in the future. Gut, yeah, the brain-gut axis. That's a great question. It's a, I won't say it's a hot topic, but certainly it's an area that has gotten a fair amount of it's gotten a fair amount of attention in our field at least. I would say that the what to do with that bill. So yes, it is obviously the case that bacteria in the gut manufacture a lot of peptides, a lot of molecules that make their way into an individual's plasma circulation. But what are the how to classify, let's say, different groups of gut metabolic products is difficult. Number one. And number two, to identify exactly what effects these might have is likewise difficult. So it's an area that people have paid attention to, but there's no coherent, generally agreed upon set of criteria. This set of molecules does this. This set of molecules produced by gut bacteria does this.
Sure.
So it's hard to be concrete about the question. Anyway.
Okay, thank you. I actually have a question myself. So should we think of a causal relationship between the amyloid beta plaque producing the tau tangles and the tau tangles then producing the neurodegeneration? Has that been established, this causal relationship?
Yes. So controversial.
Yeah.
It's a little bit controversial in the way, I think the way to think about this is as follows, and without getting into too much detail. So it is true that tau tangles appear in a very small confined area in the brain early on. That is the entorhinal cortex and hippocampus. So these are areas in the medial temporal lobe. They appear in those areas in autopsy studies early on. But in the absence of amyloid, beta amyloid, they don't progress throughout the cortex. Mm-hmm. So the way I've thought about this disease, and this is, show this graph. Yeah, so you can see in this graph right here, you can see this line right here, detection threshold. So this would be the point on the y-axis where these different biomarkers would be detectable. And you can see that there's some movement beneath the detection, beneath the threshold of detection here. So in earlier versions of this graph, the tau line actually sits above the amyloid line here early on. But the way I've thought about this, and a lot of people in the field think about this, is that the initial appearance of tau tangles in the medial temporal lobe happens as a function of aging. But in those individuals who develop a fair amount of amyloid pathology, beta amyloid pathology in the neocortex, that does something to tau dysmetabolism. And what it does is it promotes the progression of tau from medial temporal lobe areas throughout the neocortex. And in fact, it really looks like the tau tangle proteinopathy is what winds up killing neurons. Mm. So there is this sequence of tau initially appears for its indolence, but in the presence of amyloid, it gets driven out of the medial temporal lobe, and so amyloid then enables this spread of tau, and it's tau that is the proteinopathy that
Okay.
winds up killing neurons.
And related to that, should we think of the tau tangles as sort of a localized spreading, like the way cancer spreads from a region and then migrates outward, or is it a global thing? If you have a tau tangle in one region, you have a greater risk of having it showing up somewhere else.
So another great question. And there are two schools of thought to how tau tangles spread. So I didn't mention any of this, but of course in the neuroscience literature, there is this notion of network connectivity. So in other words, you can imagine functional hubs that are connected by axons. So it's sort of the node and you can think of it in terms of graph theory, nodes and edges for spread of tau. So one school of thought is that tau spreads, and it's very clear tau spreads. One school of thought is that tau spreads along these functionally connected network connections. So one area of the brain is functionally connected to another, and it's the spread along those functional axes or functional pathways, if you will. And that's how tau spreads. Pathologic forms of tau spread from one neuron to the next, to the next, to the next, along these connected pathways. There's a second school of thought, which is its local spread. You imagine putting a drop of ink into a pool of water, it diffuses concentrically through the water. And I would say that most of the thinking in the field gravitates towards the former mechanism. And that is the tau spreads from one neuron to the next along these connected functional pathways.
That's very interesting. Okay. Well, thank you very much, Dr. Jack. So this was a beautiful talk. Thank you for answering the questions. So to all of you who've joined us, thank you for joining. We'll stop the public part of the lecture now, but if you'd like to ask questions in private, please stay around for a few minutes, but I'll stop the recording. Thank you for coming, everybody. Have a great weekend.